Okay, so today our aim is to talk about another integration technique. It's called integration by partial fractions. And at the end of last Thursday, I mentioned that we would be doing this and that it's really not a calculus technique. Right? It's a technique you can do just with algebra, but which we can apply to calculus problems. To motivate these things, let me first remind you that you know how to integrate a very nice class of functions. So let's look at an integral like this. We're here, A and B are nice real numbers. So now that you've worked through all these nasty integrals, this easy one shouldn't faze you too much. What would I like to do to solve this? Substitution, exactly. And what would be, say, my u? Ax plus b. Okay. Not so many choices. Okay, and so what will my du be? Just a, right? A dx. Okay. Or if you like, dx is du over a. Okay, so we can rewrite our integral as, well, let's see, the dx becomes du over a, and I'll just pull the a out. And I'm left with du over u. And this isn't that bad. Right? So I get 1 over a times, what's the integral of du over u? Natural log, absolute value of u, right? Plus c. And then I can, what would you say, unsubstitute or resubstitute? Fill in the blanks. Okay, so this is very nice. Whenever we have an integral of the form dx over ax plus b, we can immediately write 1 over a ln of the absolute value of ax plus b plus a constant. Yep. Okay, so it would be really nice if we could take integrals and put them into this form. Right? Because once we get into this form, boom, we know what the answer is going to be. Okay, this is our motivation for studying the partial fractions method. Right here. Now, before I tell you what partial fractions is, I need to just give you a brief review of something about polynomials. Okay? Remember, polynomials are things that look like 2x cubed minus 4x squared plus a half x minus 1. You know? It's a nice polynomial. And let's say I have another polynomial, but I'm not going to tell you what the coefficients are. I'm just going to give them names, A, B, C, D. And let's say that I know that these two polynomials are equal. What are A, B, C, and D? Okay, what's A? 2. Yeah? What's B? -4. What's C? And what's D? -1. Okay. So what we're getting at is that two polynomials are equal if and only if their coefficients are equal. Okay. Let me give you another example. I like the way this is all funneling down. let's say I have x squared plus x plus 1 equals ax plus b. Does this make any sense? What's wrong with this expression? It lacks a term, right? It's missing an x squared term, right? And this definitely has an x squared term. Okay, so this can't be the right way to write it. Okay. What if I did it the other way, though? What if I had ax squared plus bx plus c, and I have x plus 1? Can this be right? How can it be right? What are my a, b's, and c's? A has to be 0, right? That's an allowable real number here, right? So this has no x squared term, so this can't have an x squared term. So that's 0, and then b and c are both 1. Okay? Okay, so we're going to need this, because we're going to create situations where we have polynomials equal to each other, and then we need to be able to say, therefore they have the same coefficients. Okay, very nice. So let's start with an easy example. What are we trying to do? Well, let's say I have this integral. Now, if I had a plus in here, what would the answer be? Arctan. Excellent, right? We know exactly what to do. But what happens with a minus? Well, you think substitution maybe, and you go, okay, u equals 1 minus x squared, but then you get this derivative as minus 2x, and there's no x up top to cancel out. We might try a trig substitution. Right? And actually, if you recall when we did trig substitution, do you remember what this went to? That's right, it went to secant. So remember, if we set u, or x rather, equal to sine of theta, then what is 1 minus x squared equal to? Think Dina. Cosine squared, right? Because x squared is now sine squared, and 1 minus sine squared is cosine squared. That's the Dina trick. Right. And what's dx equal to? Cosine theta d theta. Which means we could rewrite this as, well, let's see, dx is cosine theta d theta, and 1 minus x squared is cosine squared theta. One of the cosines will cancel, and we're left with 1 over cosine of theta d theta, and of course 1 over cosine is, as Kaiway said, secant. Well, that's a perfectly good integral. What's the problem with that integral? Just a small, tiny problem. We don't know what it is. We don't know what the integral of secant is. Right? So we've replaced a perfectly good integral that we don't know how to solve with a perfectly good integral that we still don't know how to solve. So at some point, we've got to solve one of these two. And today, we're going to see how to solve this side. The upshot is once we've done that, we'll now know how to solve the integral of secant. Okay, so how can we do this? Well, what do we know about 1 minus x squared? Just as a function. Is there anything we can do with that? We can factor it. How does it factor? Exactly. It's a difference of squares. So it breaks up as 1 minus x times 1 plus x. Of course, we can invert this. No problem there. So integrating this is the same as integrating that. And, well, isn't this right? If I just have an integral of a, well, this is like a product of fractions, right? The integral of a product is the product of the integrals, right? Is that right? If I have the integral of sine of x times e to the x, I can just write it as integral of sine of x times integral of e to the x. Is that right? Lace says no. Dean is nodding. Who's right? Can I just break this up? Well, this would be really convenient, right? Does it work for derivatives like that? If you have the derivative of a product, is it the product of the derivatives? Or do we have a special product rule that makes things more complicated? All right. And what did the product rule turn into in integration? By parts, integration by parts, right? If it was so easy, right, we wouldn't need integration by parts. Okay, so this is nonsense. Okay, we can't do this. All right, so that means that we can't just break this up as a product. Okay, it would be so nice if we could, because each of these is really already in this form over here, right? Okay, the 1 and the x are in the wrong places, but that doesn't matter, right? Make it minus x plus 1, x plus 1, right? Whatever. Okay, so if we could just break it up as a product, oh, it would be so nice, but we can't. Okay, so if we can't break it up as a product, what would be the next best thing? If we could break it up as a sum. Right? If we could say 1 over 1 minus x plus 1 over 1 plus x. But of course, this is absolutely ridiculous. You can't just take a fraction, right, and have something on the, I mean, if you would, 1 over 3 times 5. Is this equal to 1 over 3 plus 1 over 5? Of course, this is nonsense. You can't do that. It's ridiculous. Okay, fine. But what if instead of 1 over 3 and 1 over 5, I allowed myself to change this numerator into a different constant? Right? Now, if I change it into a different constant, I don't really care, because when I integrate, constants just come out. So if I put an a there and a b there, could I do it? What would be my a and b? Let's see. Remember, we have this trick for adding fractions. At least 40% of you weren't here to see it last time. So let me just quickly give you the rundown on how I add fractions. Right? Most of you find common denominators, and that's all fine and good. But it's a pain in the rump. And there's a definition of addition of fractions, which is actually quite sufficient for the purpose of adding. What you do is you do diagonally a times d plus b times c divided by b times d. That's the definition of addition of fractions. Okay? Now, it may look complicated, but let's do one in practice. Let's say you wanted to add, well, say a third and a fifth. Well, you do 1 times 5 is 5, plus 1 times 3 is 8. Well, 1 times 3 is 3, but we added the 5, that's 8. Over 3 times 5 is 15. Okay? 1/3 plus a fifth, 8/15. Okay? Much easier than finding common denominators and fiddling around. Okay. So over here, if I wanted to do this, I would get 5a plus 3b over 15. Of course, right, this is 15 on the bottom. So I just need that 1 is equal to 5a plus 3b. So you just need to find a and b such that 5a plus 3b is 1. There's actually a lot of choices that you could make for this. So for instance, what if I made a equal to 2? So that'll give me a 10. Right? And then I need to somehow get back to 1, so I can subtract 9. And the way I can get 9 is by making b minus 3. Right? So 1 over 15 could be written as, well, let's see, a was 2, so 2/3. And then that plus here, well, really becomes a minus. Minus 3 over 5. by the way, in this formula, if you have a minus instead of a plus, that just becomes a minus there. Okay, so this is actually quite cool because, all right, I've now taken this one fraction and broken up into small fractions with smaller denominators. Right? Now, of course, we're not trying to integrate 1/15. We're trying to integrate 1 over 1 minus x squared. So we want to try to play that same game with this. Right? Think of these as your 3 and your 5. Right? We just need to break it up and figure out what these constants on top are. Okay, so let's give it a shot. So we want to write this as some constant over 1 minus x plus some constant over 1 plus x. Of course, once we do that, we're going to be in this case where if we wanted to integrate this left side, we can now integrate the right side term by term. And we can use this first formula that we computed. Okay, anybody know what A and B are? Well, guessing is always a pain, yeah. Makes you feel so bad when you can't figure it out. And if you do, you don't want to say it out loud because then everybody's going to think you're a nerd. And that's always a problem. I know you guys have reputations to maintain. Okay, so well, let's see. Part of the thing that makes this annoying is that we have fractions. And fractions are always troublesome. So how can I get rid of the fraction? I could make them negative exponents, but then, of course, I've introduced negative exponents, right, which are frustrating as well. I just want to get rid of fractions, negative exponents, everything completely. I don't know how to integrate. Multiply both sides by this denominator. Right? When I do that, it'll kill these two denominators. Now I'm going to pick up some extra junk on top. That's kind of annoying, but that's the nature of the beast. Okay, so if I multiply through by this denominator, then the left side will just become 1. All right. And what will happen to the right side? Let's see, when I take this denominator and multiply it here, the 1 minus x's will cancel. Right? But the 1 plus x is just going to get left on the top. So I'll end up with a times 1 plus x. Okay, and then when I multiply this denominator here by the right term, the 1 plus x's will cancel, and I'll be left with a 1 minus x times the b. Okay, that looks a lot simpler. Right? Everybody thank Jenna. Okay. All right, so now what I'm going to do, and you're always going to do this every time you do this partial fractions trick, right, is you're going to expand it out and then reorganize. Okay? Because what you want to do is turn this into a nice polynomial. Because on the left you have a polynomial. It's not a very interesting one. Right? But on the right you should also have a polynomial. And we already saw what happens. Right? When you're talking about polynomials, if two of them are equal, then you know they have the same coefficients. Right? And that's going to give us information about A and B. So first I expand this. I get A plus AX plus B minus BX. And now I'm going to combine all the x's and all the non-x's together. Right? So for instance, here I have an x and an x. So I get AX and minus BX, so this becomes A minus B times x. And then I have an A and a B. So I don't really need parentheses there. I just want to make sure you can see these two different terms. Okay. So what can you tell me about A and B? right, a minus b is 0, and a plus b is 1. Why? Why? Yeah. What's the x term over here? Well, there isn't one. It's 0. So the x term over here has to be 0. So a minus b has to be 0. The constant term is a 1. So the constant term here has to be a 1. So a plus b has to be 1. So we've reduced our situation to solving a system of two equations with two unknowns. This is a particularly easy one. If a minus b is 0, what does that tell you? A equals b, right? A minus b is 0, then a is equal to b. Okay, so a is equal to b, so this becomes a plus a equals 1, which is 2a equals 1, which means a is a half, and of course a was equal to b, so b is a half also. Ho, ho, ho. We have found the one and only one way of breaking up 1 over 1 minus x times 1 plus x as something over 1 minus x plus something over 1 plus x, where something is a real number. So this is, right? Well, a is a half, yeah, over 1 minus x, and b is a half over 1 plus x. And now we're in really good shape. Because whereas we didn't know how to integrate the left-hand side, we know exactly how to integrate the right-hand side. So let me leave this formula up here for right now. So we wanted to integrate dx over 1 minus x squared. And we just saw that, well, if we rewrite this as 1 minus x times 1 plus x, we can actually break this up into two different integrals. The first one, we're going to integrate a half over 1 minus x. Of course, what am I going to do with that half? I'm just going to pull that out, right? I'm not even going to mess with it. So I get a half the integral of dx over 1 minus x plus, get another half, the integral of dx over 1 plus x. Yay! We can do this. Okay, so it might help to use this formula, right, if we just rewrite this as minus x plus 1, because then it's, we can see it's in the right form. You know? Looks just like this. So you have ax plus b. So here a is minus 1, and b is 1, right, in this first one. Yeah? So this first one is going to give you a half natural log of the absolute value of, well, minus x plus 1. Right? But we forgot. There's a minus. We have to do 1 over a, right? A was minus 1. So we actually pick up a minus sign. Right? That comes out front. Then plus. Well, if we like, we can rewrite this as x plus 1, if it helps us. Okay, we get 1 over a, but here a is just 1. So that doesn't change anything. So we just have a half ln absolute value of, well, x plus 1 plus our constant of integration. But wait, there's more. If you act now, we can simplify this expression. So first thing, you see I got these minus 1 half, and this half out front of a log, right? What can you do with something that you multiply into a log? You can pull it up, right, into the exponent. So this becomes natural log of absolute value of x plus 1 to the minus 1/2. Actually, I don't want to pull the minus. I'm going to keep the minus out front. I'm going to do something with that in a second. Plus natural log x plus 1 to the 1/2. Now here I have ln of something minus ln of something. Yeah? And what can you do if you have natural log minus natural log? You can make it into a quotient, right? Logs turn division into subtraction. Vice versa, takes subtraction, turns it back into division. So this is equal to the natural log, okay, of x plus 1, right, like this, x plus 1 to the 1/2, divided by minus x plus 1 to the 1/2. Right, let me get some parentheses around here. And then, of course, plus c. Or, well, you notice here I've raised both of these things to the 1/2 power. So I can pull that 1/2 out if I like. And just do both of these at the same time. So first, do x plus 1 absolute value divided by minus x plus 1 absolute value. Then take the square root, right? And then take the logarithm. Yeah? Okay, that's not a bad place to be. It's a nice, simple expression. Well, simple, you know. I'm not telling you to memorize this, by the way. Right, this is not worth memorizing. However, what does this also tell us? Yeah, we now know how to integrate secant. Of course, there's a problem, right? So let's keep that. Okay, everybody got the derivation? Okay. By the way, this is the method of partial fractions. You notice there's no calculus in here. This is just, it's really just algebra. Okay, so if we start on this side, we can go this way, and we end up at that integral. And, well, if we snake our equal sign out here, we know that this is equal to, we just got natural log of, well, for the time being, let me pull this half out just so I don't have to deal with it till the end. The nice thing about these logs, right, I can always move these exponents back and forth. Okay. So, in fact, I'll even, well, it doesn't really matter. I'll put these absolute values around the whole thing for now. Okay. Absolute value doesn't care about division. You can put it in or out. Okay, here's the problem. I started with a theta, and I've ended up with an x. Okay, that's not good. Okay, so what was x? Well, x was sine of theta. So this is a half ln. Oh, I feel like we've made a, sorry, I wrote x minus 1. This should be minus x plus 1. Right? And, well, I hate writing my negatives first because it's always confusing. So let me swap these around. I'll just make that 1 plus x and that 1 minus x. It's really back the way that, well, we originally had it over here. Okay. Okay, so then I get sine of absolute value of 1 plus sine of theta. I'm sorry, ln of absolute value of 1 plus sine theta over 1 minus sine of theta. And this didn't look so bad with x's But with sines, I don't know, somehow this doesn't look as nice anymore to me. Anybody get that weird feeling? All right, so let's play with this for a second. Okay, so let's look at, and let me use my normal convention. S becomes sine theta. Yeah? So I just write this as 1 minus S over 1 plus S. Okay? This is my usual convention. You're okay? Not bothering anybody? Okay, so S is sine theta. Okay, so how would you simplify that expression? Oh, I know why you're looking at me funny. What can you do with this? It's a nice trick when you have, say, on the bottom, something minus something. Multiply, right, top and bottom by 1 plus S. And of course, it's fitting that Dina suggests this, because what's the bottom going to look like? 1 minus S squared, which is cosine squared. Okay, and the top, well, it is what it is. 1 plus sine squared. Okay, over cosine squared. Okay. Something nice is happening here, though. Well, you see this half that I have out front? I could throw that back inside again. Yeah? Now, if I throw it back inside, what's going to happen? Well, let's see. 1 plus sine theta over 1 minus sine theta becomes 1 plus sine squared over cosine squared. And now I take this half and I put it back up top. What is that half going to do in here? Ha ha ha. It's going to kill those squares. So I get 1 plus sine, right, over cosine. All right. And if I go a little deeper, well, I have something plus something over a nice denominator, so I break that up. Right? 1 over c plus s over c. Different c over here, by the way. No? Okay, and what's 1 over cosine? Secant, right? Which I'll write out in full to avoid confusion. And what's sine over cosine? Tangent. So we now have a very nice formula. The integral of secant of theta, d theta, is the natural log of the absolute value of secant of theta plus tangent of theta plus c. Now, this is why you shouldn't feel bad that we couldn't, cook this up with a nice, easy, substitution or something. No? Okay. So why don't we start a little chart? Okay. Why don't we start a little chart with all of our trig functions on it? Because at some point we need to know what all the integrals of the trig functions are. Well, these ones we can do. Yeah. I'd prefer to put cosecant first. All right. So it's about time. So what's the integral of sine? Negative cosine. Okay, and the integral of cosine? Sine, good. Okay. Anybody know what the integral of tangent is? Okay, well, think about it. Cosecant we haven't done yet. What about secant? That we know. So integral of secant is natural log, absolute value of secant of theta plus tangent of theta. See? Note one really nice thing as far as remembering this. I'm not suggesting that you have to memorize it, but if you wanted to, you remember the derivative of secant with secant tangent. Same functions that show up. Right? And secant is 1 over cosine. Now, when you integrate 1 over x, you pick up the ln. So it's not a huge surprise that you pick up an ln here. Right? So there's a lot of synergy with what you already know. Okay, and cotangent, well, we still don't know that one either. So we have half of the chart. So we need to work out the rest of this thing. Which one do you want to do first? Tan? Okay. As you wish. Since it's reasonably important, let's keep this formula up for later reference. Okay, so I want to integrate tangent. Any ideas? Okay, if you insist. Okay, tangent is sine over cosine. So Dina suggests turn it into sine over cosine. Okay, how do we integrate? Boy, when you see sine and cosine in the same thing, that really makes you want to do something. U substitution, exactly. All right, so what should my u be? I have two choices, right? It's either sine or cosine. Now let's think what happens. When I make u one of them, when I do du, it's going to give me the other one, and that will be on top, right? It'll be on top. So you actually want to make the u the one on the bottom so that you get this one on the top as part of your du. So we'll make u equal to cosine of theta. And so du will be negative sine of theta, d theta. Okay, so let's see what happens. Well, see, on top I have sine theta d theta. And if I just had one extra minus sign, I'd have du. So I'll just toss a minus on the front and a minus on the inside, and then I'll get a du. And then on the bottom, I just have u. And, oh, that's not so bad. We've played this game before. It's just the natural log of the absolute value of u plus c. We've got this little minus out front. And of course, u, we said, was cosine. Well, that's not bad. But notice I have a minus in front. That's kind of annoying. What can I do with that minus? Think of it as a minus 1 times a logarithm. What can I do? I can bring it up. Now, why would I want to do that? That's just going to make that to the minus 1 power, which means 1 over cosine. Why would I want to do that? That's secant. Okay. So I can, at the cost of using a function that we usually don't like as much as cosine, I can drop that minus in front. And there's always a synergy, right, between tangent and secant. The derivative of tangent is secant squared. The derivative of secant is secant tangent. We just saw that the integral of secant was ln secant plus tangent, right? So it's really fitting that the integral of tangent should be the natural log of secant. And notice again, tangent is defined, right, as a function divided by another function. And they're not just any two functions, right? Sine up to a minus is the derivative of cosine. Whenever you're in that situation, right, we saw when you have u prime over u, right, and we integrate this, okay, this is going to end up being ln of the absolute value of u. Right? Because you can do a substitution, right, if you like. Or if you like, take the derivative of this. It's 1 over u times u prime. 1 over u times u prime. Okay, I've left out a lot of extra notation here, but you get the idea. Okay, so we can fill in our chart. Tangent is ln, the absolute value of secant of theta. Okay. What's the next one we should do? I didn't say what's the next one on the list. I said the next one we should do. There's only 2 left. I just criticized your choice of 1. You're going to go with cotangent now? Okay. Okay, now, why is cotangent going to be easy? It's exactly the same thing, right? You have, instead of sine over cosine, you have cosine over sine, right? So let's see. If you do cosine of theta over sine of theta, oops, I already have the of theta, and I guess we need cot. Then, of course, I'll want to make my u into a sine, and my du will be a cosine. And, well, let's see. Cosine of theta d theta is du. So I already get that. I don't need the minus sign. And then I get over u. So everything's the same, except I get this minus sign dropped. This sine, cosine turns into a sine. And that seems to be the end of it. We make any mistakes? U is sine, du is cosine, du over u, ln absolute value of u, ln of sine of theta. No? It's so easy. It's what Axl Rose said. It's so easy when everybody tries to please me, baby. Okay. So we just have one left on the chart. Cosecant. Anybody want to guess what method we're going to have to use to do cosecant? Partial fractions. Okay, so let's see if we can mimic what we did for secant. So secant is 1 over cosine. So cosecant is 1 over sine. All right. And I don't want a cosine squared down here. I want a sine squared. And I don't want a cosine up here. I want a sine. Okay, now is it still true? Yeah, sine over sine squared is 1 over sine. It's still true. I'll slow down because I realize I'm erasing, which makes it much easier for me, but you have to write this off. So I'll give you a second to catch up. So we've done this. Now we want to translate it back into this form. To do that, I need that 1 minus x squared is sine squared, which means my x should be cosine, and my dx would then become minus sine. But I have to be careful. I have to be careful. If I started from here, and I said let x equal cosine of theta, then it's certainly true that 1 minus x squared is sine squared theta. And then dx would be minus sine theta d theta. No problem. Now, to go from here to here, I would say, okay, so dx is minus sine theta d theta. Oh, I don't have my minus. Right? So I'd have to put a minus over here. But I don't want a minus over here, so instead I'll put it over here. If I put a minus over here, well, now I could write minus dx. And minus dx is sine theta d theta. So this is really quite remarkable. And it follows my law of Co, which is if you want to integrate cosecant, it's the same as integrating secant, but with an extra minus sign. Now our answer is going to end up a little bit different because we chose a different x. Okay? But effectively what you're doing is saying, yeah, when you integrate cosecant and secant, it's really the same idea. There's just a minus sign that pops up. And of course, as usual, the minus sign pops up on the co. Okay, so this means everything we did to integrate dx over 1 minus x squared works exactly the same. There's no change needed. Right? And we got that this was the integral. Right? The only difference here is we have a minus, so we have to toss a minus out front. Now we need the eraser. That way we look. So we're up to here. Yeah? I haven't actually erased a whole lot yet. So we're still getting to this bit. So here, that was a secant, became a cosecant. That was a cosine, became a sine. All these cosines turned into sines. Basically, all the sines and cosines got swapped. And that was it. And we added this minus up here. That's all we did. And then we have a minus that pops up here. All right. Are we caught up writing? Okay. So now, what happened in the next step? Well, in the next step, we substituted back in for x. And we said, oh, x is sine theta. But now x is cosine theta. So this has to become 1 plus cosine theta over 1 minus sine theta. And there's an extra minus now in the front. Then remember we did this trick. And this trick works exactly the same with all the s's and c's swapped. Right? Because that function, that equation sine squared plus cosine squared equals 1 is symmetric in sine and cosine. Okay? So that means on this next line, I can just take all my s's, turn them into c's, all my c's, and turn them into s's. And I still have, I'll take this minus and just leave it out front for now. Now in the next step, we took this half that had been sitting out front and put it up top so that we could kill these 2's. Right? So we kill those 2's. And of course, these c's and s's need to get swapped. And then we broke this up, 1 over s and c over s. Okay. But now these c's and s's get swapped. And actually, before I... no, just leave it like this. So, okay, we can break that up. And so at the very end, okay, I get 1 over sine, which is cosecant. And I get cosine over sine, which is cotangent. And now I'm bothered because there's a missing minus sign. All right, so where did we miss our minus sign? Yeah, this should be, I'm wondering if maybe this minus has popped in here somewhere. See if I wrote this down. No, I don't think I did. Okay, so there's a hole somewhere in here. We've made just a minus sign problem. Right? The answer should have a minus sign right there. Okay, so 5 bonus points. Anybody who can go through this in detail and tell me where the problem is. Okay, good. It's got to be in there somewhere. Maybe you just need to throw this minus in somehow. Okay. So up to a little problem that I leave it to you to resolve. The integral of cosecant should be natural log of cosecant of theta minus cotangent of theta. Do you see it already? Yeah, this negative should somehow disappear too. I mean, somehow this negative needs to go inside. Actually, maybe that's the... I mean, this may not be wrong. Okay, this may not be a typo as much as... Okay, let's try this. Yeah. Let's take this negative in right at this point. And we put it in, that's going to raise this to the minus 1, which is just going to flip it. Right? So instead of having 1 plus cosine over 1 minus cosine, you're going to have 1 minus cosine over 1 plus cosine. Okay? Whenever you take something like a over b and raise it to the minus 1, this is the same as b over a. Okay, so then we would have 1 plus cosine over 1 minus cosine, but it would be flipped. So you get 1 minus cosine over 1 plus cosine. We play the same trick. We're going to multiply by 1 minus cosine top and bottom. And that'll give us 1 minus cosine squared on top. And 1 plus cosine times 1 minus cosine is 1 minus cosine squared. What's 1 minus cosine squared? Sine squared. So 1 minus c over s squared. Okay. So then here, this minus would go away. This would be a minus sign. This half would kill these squareds. This is still would be a minus. This would become a minus. That minus would go away, and this would become a minus. Ha! I get the 5 bonus points.
I pointed it out.
Oh, okay, that's fair enough. What did you point out? I don't know, raise your hand if you think Lath deserves the points for that comment. All right. That's 5 out of 5. That's okay. Lath gets the bonus points. Very good. Okay, good. So actually, what this shows is actually we didn't make a mistake anywhere. Right? This is just a different way to put it. You can either have the minus out front and the plus inside, or the plus out front and the minus inside. Good. Now you feel better. I hate making mistakes. Okay, so this is very nice. We now know the integrals of all of our trig functions. This is good, right? This is good. All right, so let's go. Let's see, what time is it? I just want to start off. This, by the way, none of this was in my notes. This is what I was thinking on the way over from Fenton to this class. I said, this is what we should do first. so now we'll get to what I'd planned. Let's do one more example before we generate the general theory here. This one is so long that I actually have to write this down. All right. So I'd like to integrate this very interesting expression. And I want to do it using this partial fractions method, meaning I want to break this up into two different fractions, right? One which has a denominator x plus 4, and one which has a denominator x minus 5. Right? And hopefully, if I'm lucky, I can then use this sort of trick. So that means that I need to take this fraction, right? I forget I have a calculus problem. And I want to write this in the form, well, that I would like to write it. Now this is what I would like to do. All right, so how did we solve this problem last time? Yeah, we got rid of the fractions, right? We multiply through by the denominator. So if I do that on the left, I'm left with x minus 23. And on the right, let's see. This is going to kill the x plus 4, but it's going to leave behind an x minus 5. And this denominator will kill the x minus 5, but it'll leave behind an x plus 4. All right, so now we lift and separate. Is that funny, Colin? Okay, so lift and separate. Ax minus 5a plus bx plus 4b. Okay, that's the lift, and now we separate. So I have an ax and a bx, so it becomes a plus bx. And I have a minus 5a and a 4b. So I have ax plus bx. So it becomes a plus b. Okay, so let's do a little side work. What can I conclude from this equation about a and b? A plus b, and, well, I can say something about minus 5a plus 4b. What's a plus b? Why 1? Yeah, right? This is a polynomial, this is a polynomial, and they're equal. So they have the same coefficients. Coefficient of x is 1. Coefficient of x here is a plus b. So a plus b better be 1. Right? The constant term on the left is minus 23. So the constant term on the right, which is minus a plus 4b, has to be minus 23. So now we just need to solve these two equations. All right, well, let's see. If a plus b is 1, then what is b? 1 minus a. Right? Okay, so I can plug that into my second equation. So I have minus 5a plus 4 b's, but b is 1 minus a, so I get minus, or plus 4 minus 4a. Minus 5a minus 4a is minus 9a. And if I take this 4 to the other side, I get minus 27. Dividing by minus 9, a is equal to 3. And since b is 1 minus a, b is 1 minus 3, which is minus 2. And so I can write 3 over x plus 4 minus 2 over x minus 5. Okay, now this takes some practice. And it's just algebra, but it takes a little bit of practice, right? You'll make some mistakes. And how do you know you've made a mistake? Well, at the end of the day, you get your a and b, and you can actually recombine these, right? You have two fractions. You can subtract them, right? If you think, oh, how do I even find common denominators? Don't. Use this formula. Use this formula. And of course, you know what the denominator is going to be already. It's just the product of the two. So you don't have to worry about the denominator. Right? It's already just going to be this product. You just have to do 3 times x minus 5, right, minus 2 times x plus 4. Right? So this becomes 3x minus 2x, which is x. Then you have minus 15 minus 8, which is minus 23. X minus 23 is exactly what you wanted. Okay? So you can test this. Okay? But the other nice thing is we can now solve this integral. Right? This is now going to be two integrals. Well, let's see. The first one will be 3 over x plus 4, but of course that 3, pulling that bad boy out. Right, then I get, well, minus 2. That's just going to come right out. And, well, lo and behold, look what happens. All right? This integral is just going to become ln of the absolute value of x plus 4. This one will become ln of the absolute value of x minus 5. And since there's nothing in front of the x's, right, you don't have to worry about a 1 over a. So that's nice. So you get 3 ln absolute value of x plus 4 minus 2 ln absolute value of x minus 5 plus c. And if you're into the whole brevity thing, you can take this 3, fire that up. Take this 2, fire that up. Then you have a log minus a log. And what can you do? You can turn it into a quotient, right? So you can actually make this one logarithm, absolute value of x plus 4.
Excuse me, I can verify you didn't answer evaporate before.
Oh my gosh. Okay. Over x minus 5 squared plus c. Very good. Okay.